Hi, this is Bharat. I'm currently pursuing BE Mechanical Engineering at Coimbatore Institute of Technology. Now I'm going to discuss about the topic is thermal aspects in metal cutting process. Let's we go to the topic. First, we are discuss about then learning objective. What we are learning in this topic, we are these are then heat generation, temperature distribution, and measuring of the temperature and controlling of cutting temperature and cutting fluid in machining. We are discuss about the topic in later. First, we discuss about in heat generation in metal cutting. First, thermal aspects mean we will find out then how much of heat is generated and what is the temperature. These are then we are find out the thermal aspects in heat generation topic, heat generation process. First, there is then some type of mechanical energy was literally converted into the heat. Like an heat is maybe generated in the machining process, like an tool and workpiece. In between there are the different types of heat was produced in then different types of areas. First we going to then first thing we going to then in this image we will see then image. There is then A zone and B zone and C zone. There are different types of zones are involved in the process. First, A zone is then shear zone and B zone is then chip tool interface zone. Because of then this is then chip, this is then chip, and this is then tool. There is then interface of then in between of then to chip and tool. There is then some sort of heat was generated. And third is then B. B is then workpiece and tool interface. Either in between then workpiece and tool, there is then some sort of little bit sort of heat was generated in this process. First, why the heat is produced in the frictions of two metal, the heat can be generated. Like in between the tool and the chips, it can be a little bit of a heat was generated. Like in workpiece and tool, in the rubbing area of the tool and workpiece, it will some amount of heat was generated. In this process of thermal aspects, there are three types of heat was generated in the process. First, A is then shear zone. The shear zone of the metal cutting metal is there are lot of heat was generated, like an 80 to 85% of heat was generated in this process. Like we will see in the image, like the metal was separated into the workpiece. In the area, there is the most of the heat was generated in the process. And another part is then b part is then tool part is then 15 to 20% of it was carried out in the place. Because of there is then separation of the chip is small lightly slide out in the tool. It was created in some rubbing, and then rubbing to create it in the friction to generate in heat in the process. And third one is, and then little bit of heat was created, and already says in the rubbing area of the tool and workpiece, there are little bit of 1 to 5% of heat was almost created in that place. Like there are different types of create in the heat in this place. In the friction we can increase in the process. There are different types of variables of heat was created in the area. Because of cutting, we are increasing the cutting speed, the temperature was increased, and also the friction also increased, and the temperature almost they gradually increase in the process. Like, and also cutting feed, we are increasing then cutting feed, then also temperature was increased. Because of then tool and workpiece is then very smallly to go, they it was damaging the surface of the workpiece. And third one is depth of cut also will increase the temperature. Because of you will see in the workshop, there is then chips are flying into the air. Because of then the tool speed was increased in then gradually increased in the process. Then it was moved into then very forcefully. Because of the tool was it was flied in like in spark to fly in the air. In some area we are seeing about then some of blue color and dark blue color chips are formed in the workpiece. Because of there are high temperature of heat is produced in the area, there are lot of heat was produced. Because of then oxidation was created in that area, then it was damaging, it was shown into the chip was a little bit of dark and high darking chip was created, dark color chip was created. Because of that it was showing that high temperature are created in that area. We are reducing the temperature, it was increasing the two lives. We are seeing about then upcoming topics, upcoming areas. And let me go to then another process. And like we do in the slide, why do we want to know then cutting temperature? because of we are knowing then machining performance. We are knowing the machining performance. We give a particular tool in that properties to give in the machining to use to measure the temperature in that area. We will give then different types of and different properties materials of the tool was used in the different areas. We will see in the upcoming slides. And next one is tool designing and selecting the cutting tool. I'm already says there are different types of materials are used, different types of workpiece materials are used, like in cast iron, steel, and aluminum. There are different types of tools also used. Because of the tool materials are very hard and very tough materials we are used in the tool. In workpiece there are very small material, very less hard material. It was easily to cut the metal, and tool was not the temperature was not increased, but it is the very hard workpiece. The tool was moving into the workpiece. It was created in a high temperature. It was damaging the tool. Because of we are selecting the high speed tools. Like, and another one is to find then thermal stress. Here different types of stress was created in this tool was moving into the workpiece. There are different types of strain and strain rate, and different types of properties are created in that process. These are then formulas to calculate the cutting temperature to use in then different types of derivations are used to calculate the cutting temperature in the moving speed and feed and the depth of cut. We are calculating the different temperature. Okay. And next topic. And this is then we are using into then it is an analytic image of then cutting process. Like you will see in the process, there are tool is cutting into the metal. In the it was moving into then towards of the tool. There are different types of temperatures are created, and analytical image was shown in the process. There are different type of energy was created in like that. See in the nearby then edge of the tool was the most of the heat was created in the process. Because of we are damaging the tool edge. We are changing the different types of method to use and damaging the tool edge of. This is the method to use to calculate the cutting temperature. Which type of tool is good for that working area. We are calculating in that process to used in the method. Like then temperature distribution in the workpiece in this instantly then shift zone as well. And then typically experimental study in the figure. It is then experimental study. We are going to the upcoming areas. Next, why what are the effect is created in the high cutting tool temperature on the tools and workpiece. It was rapid tool wear with reducing the tool life and cutting edge deformation, and it will loss the hardness. It called you will increase the feed and speed in the tool. The tool was getting highly heated. In the highly heated what it was damaging the hardness of the tool. Because of we are seeing about the quenching operation, it was increasing the hardness. Because in this form we are increasing the heat. Only we are increasing the heat, but not only cooled, not cooling in. Increasing in the heat in, we are continuously use that tool. It was damaging the tool life. And it was a built up then edge formation, surface damage by oxidation. I'm already said there are oxidation was created in the tool, in between the tool and workpiece. It created in chip. Then chip was changing the color into the dark blue, like we are seeing in the process in the working area. Like we are deformation of the cutting tool. There are a lot of deformations are involved in that. There are two type of deformations are involved, like an analytical and experimental. Analytical, we are using the different types of softwares to use to check the cutting temperature. And like an another process, it is like an you will see in the process, you will see in the answers or another type of analytical softwares are used. And this analytical method using a mathematical model to create and check the cutting temperature. It is an simple and quickly. It is inexpensive, but it is an nearby then accurate to then give the answers to the temperature was increased or lower. We are giving them software or giving them little bit near to the temperature, but it is not an accurate temperature. It is less accuracy and precision. And then experimental in the method, we are experimental method, we are lot of heat was created in between the workpiece. There are different types of method to use to calculate the cutting temperatures. And next one, and then temperature, which are of the major interests. There are different types of interest because of then area, average shear zone temperature, and then average and maximum temperature at the chip tool interface. There are, I'm already said, chip and tool interface was the major of the heat was created in that particular area. And also temperature at the working to the interface, it is like a tool flask, like a little bit of rubbing method to increase little bit of heat was created in that area. Okay. And third one is average cutting temperature. So it is, this is the major interest. So, and then next process is then how do we measure then cutting temperature, how do we measure the cutting temperature. Like we are measuring the different types of methods are used. These are the method. Then calorimetric method is then quick, simple, and it low cost, but it is an inaccuracy. Gives only a gradual average value was given in this method. And next one is an decoloring agent. It like an one type of tape or like an paint was, it was painted in the tool nearby the edge of the tool. It was you will use the tool in the operation, it was creating then it was doing the operation, and we after the operation we will check the tool, and if the tape was changing the color, there are different types of colors was changed, like an red and light red and yellow and blue and green, like that much of colors was created in that area, because of it was showing the temperature, how much of the temperature in the created in that area. You will calculate, then you will calculate is in it, but it is not much it is not much accuracy. It was a little bit of accuracy, it was used in the normal areas. And other another different types of methods are used, like an tool work and thermocouple method are used, moving thermocouple material are used, and embedded thermocouple material are used, and compound rack tool method are used. Like we see about then different type methods. First, tool work thermocouple techniques. Like a tool work thermocouple technique is then process of we are putting the tool, and another one is cold junction. We are the so difference in then we are different in the two junction. One is then hot junction. Hot junction is an tool, and cold junction is an workpiece. Like it is a lathe process. It is a lathe process. Okay. In this process we are insulated in then tool and workpiece. We are insulated in the tool workpiece because of this method is working. First we insulated in the tool and also workpiece. Because of then some of electrical losses are created, it was affecting then accuracies, giving accuracies. In the tool was hot junction is the tool, because of yours I was frictional was induced in the tool, it was created in very heat was generated in the process, it is an hot junction. In the cold junction was some of distance was in between the distance of the cutting area, then we will fix in the cold junction. And we will in between we will connect it into the millivolt meter. In between we will connect it into a millivolt meter, and it was shows then what is the temperature in between the that area. We will show into the millimeter. It was a good method to use in that area, like an it is an electrical and thermal conductivity for this techniques in which we are using the method. And next one is then moving thermocouple techniques. Moving thermocouple techniques is then it is then similar to the previous method. Like we are fixing then standard thermocouple into then in front of then in towards of then tool. We are calculating the temperature in between the tool and in between the tool. So one of this method is used in then gradually used in the area. This method is usually for studying of then gradual rise in the temperatures of continuous chips in this low chip at low at moderate cutting velocity. And next one is an inboard thermocouple techniques. And the in this process, then in the milling cutter was used in that area. Because of that we will fix in the thermocouple bed into the bottom of the milling cutter. Okay. In the milling cutter was move into the surface. It was reducing the material thickness, and in the heat was generated in highly in the thermocouple was move nearby into the um, milling cutter. It was sourced into them. It is an high temperature. It is sourced into the millivolt meter. We shows into the millivolt meter. It is then high temperature or low temperature. What is the temperature was created in the process? In the process. And next one is then a compound rack tool method. Compound rack tool method is then process of developing to measure the chip tool interface along the rack surface by thermocouple. Like we are it's similar to the first method. First method is then tool work interface method techniques. Like in the process of it is a similar method. We are using in the edge of the tool non-conductor method was used. It is a ceramic method was used in that process. In the it was conducted into the high junction. It called as high junction area. Then a lot of heat was created in that particular area. You see in the lot of here in the red mark, a lot of heat was created into that particular area. And another one of them connecting is workpiece. Another one junction is connected into the cold junction, and it connected into the workpiece. In between them two junction, we are connected into the millivolt meter. In the millivolt meter was shows into then how much of temperature was created in between the area. Okay. Next one, there are different types of temperature was created, and how to measure the temperature of in the method we are already know. We are already studied in the previous slides how the temperature was measured, and the different types of temperature was created, and which area the different temperature zone was temperatures are created, and how much of the percentage was created. Well, we are already discussed, and that controlling of the cutting temperature. We are seeing then how to controlling then cutting temperature. First one is then we are selecting of the material. Material selection is then most important process to we are reducing then cutting temperature. And another one is selecting of tool geometry. Tool geometry is then one of the method to reduce then cutting temperature. It is then physical vapor deposition like an PVD, or chemical vapor deposition like an CVD, coated on the high speed steel. It was coated on the high speed steel. It was helped to reduce the temperature by reducing friction at the chip tool at and work tool interface. It was used to reducing the temperature. And then different types of thermal conductivity of the ceramic tools are used, like in materials like in metals, carbides, or etc. like we are used. And different types of harmful gases are created in between the area. It is an affected into the it is affected into the employee health. It was an selection of tool is then most important for an cutting temperature. And another one is then like an tool geometry is then large positive taken rack angle helps into then reducing heat and temperature generation by reducing cutting force. And third one, our next point is conductant compounding rack. Compounding rack is then processed to used to break the chick, and it was enabled to reduce the heat and the temperature towards then reduce the cutting force. And these are then process to used in then. And like in another one process is we are particularly fixed then edge of the we are particular fixed then edge of the cutting tool. It was most used to reduce the heat. And next one, how to we are reducing the heat in the another one method. It is the most important method we are using in all that area use. It is called then we are using the fluid is the most important part in using to reducing it. Fluid was flow into the particular area in the then workpiece, in between the tool and workpiece. We are flowing into the fluid. The fluid was carry out then all the heat in that fluid, and it was most useful method in that process. And then lubricant and different methods are used, and then cleaning, then machining them. In that particular area there are chips are created, then frictions are damaging the workpiece surface. Then chip in the fluid was in between, then we are using the fluid in between the tool and workpiece. It was moving them very smoothly and reducing the heat. It was not affecting the working surface. It was very good and smooth surface was created in the in that particular area. And next one is there are in the friction of the method there are a lot of gases are formed, like an harmful gases are formed in the liquid was used to reduce the smoke, and it was give them better performance of the tool. Like next one, essential property of the cutting tool for cooling is an high specific heat loss and thermal conductivity and flame coefficient of heat transformation and spread and heating ability. And for lubrication it is a high lubricant, wet and spreading and high flame boiling point. There are different types of heat, like in chemical stability, low velocity, high flash point. Non-toxic gases are not involved in the process. In the winter, we are already seeing in the process. Let me showing some videos related into the cutting method. Just a minute.
There are many factors to consider when selecting which cutting fluid, if any, is appropriate for use in a given machining operation. Generally, these factors can be classified as either cutting functions or non-cutting functions. Cutting functions actually affect chip formation and influence cutting tool life, chip removal, and surface integrity. The life of the cutting tool is directly affected by the type of cutting fluid and application process used. Chip leaves the cutting zone, the longer the tool life, and the better the surface integrity will be. Surface integrity refers to the quality of the material after machining. How well the fluid reduces friction and carries away heat can have a major effect on the surface integrity of the piece part. Because of the heat and stress generated by some cutting processes, the material may be altered chemically, physically, or experience electrical and magnetic changes. Before using any cutting fluid, it is important to understand how it will react with the operator, the tooling, the machine, and the materials.
And I will show in another one video.
Cool and proper lubrication while machining is vital to being a successful machinist, but it can get tricky. Dealing with coolants can be a challenge, and that's not just because you're dealing with giant vats of liquid. Like everything else in the world of machining, there are a million different methods and scenarios to consider when choosing your cutting lubrication. First, you'll notice that I'm lumping lubrication and coolant together. Coolant is the term most often used, but the use of this substance is threefold: cooling your tools, lubricating the cutting process, and clearing chips. What you're cutting and how you're cutting it will determine how you use coolant and the method of delivery. Flood coolant literally floods, sometimes blasts, your part with this liquid. This helps get chips out of the way while also lubricating and cooling your tool. Depending on what you're cutting, the mess is typically worth it. Mist coolant is another option. It uses a combination of air and coolant to deliver a saturated mist at your cutter. This helps clear chips and lubricates, but it doesn't do much cooling. And then there's boring old air. No lubrication and only a little cooling, but it does clear those chips. So how do you know which coolant setup to use? This depends on two defining factors: your cutting tool and your stock, or the material you're cutting. For the sake of simplicity, and to keep this video under a few hours long, we'll just focus in on high-speed steel versus carbide cutters. Carbide tools can get much hotter than high-speed steel, and therefore are more susceptible to thermal shocking, meaning different parts of the cutter expand by different amounts, causing the cutter to chip, break, or even explode. This means that you typically want to go light on the coolant while using carbide tools. High-speed steel is more flexible, so no explosions, but it will still get hot, so flood coolant is recommended. Without coolant on high-speed steel, you run the risk of extremely fast tool wear or even the tool welding itself to your part. The stock you're cutting will change how you use your coolant as well. Aluminum is known to be a forgiving material because it's a soft metal, but that makes it quite gummy. So you're better off using flood coolant. Mist coolant will work, but the deeper your cuts, the more chips you accumulate, meaning more need for chip clear. On the other hand, steel is a much harder material. This generates more heat while cutting. While steel is less gummy than aluminum, the chips can still build up. With a hot cutter and mounting chips, it's best to keep things clear of your tool with an air blast technique. Now, stainless steel is harder yet, but still has some of the gummy features of aluminum, so flood coolant with high lubricity is ideal. So let's mash all these concepts together. Say we're machining aluminum with a high-speed steel cutter. You should flood the part with coolant to keep the tool cool. If we're cutting aluminum with a carbide tool, we can avoid using flood coolant because carbide can withstand the cutting temperatures without excessive wear. You'll still want to use mist coolant with high lubricity to prevent the aluminum from sticking to the tool. Deep pocketing in aluminum with the carbide tool brings up yet another possible configuration. Because we're talking about a pocket, air or mist isn't enough to clear the chips out, though you could get by with it if you needed to. Flood coolant can remedy this situation, keeping both the chips clear and the tool well lubricated. While it's ideal to have the exact coolant prescription for a given material cutter combination, you don't need to uproot your entire setup every time you cut a new material or use a new type of cutter. Your finish or tool wear or cycle time may suffer a bit, but you can make just about anything work. Check out all of our latest videos here, and for more metalworking tips, tricks, and stories, subscribe to our YouTube channel.
And thank you. Thank you for giving this opportunity to speak. And thank you.